Okay. All right. So this is going to be the first video and hopefully of many that supports our lectures, our lessons. These videos are all going to be recorded for the 2024-2025 batch, and we're doing semester two. So I'm going to have a playlist. It's going to be list out, the videos that I make, and the focus of this video is going to be questions, right? We're going to have a short review, and then we're going to practice questions. So let us begin with the first of our videos, right? Okay, the first of our videos, which is going to be on Coulomb's law. Coulomb's law, we generally focus on electrical force, right? Electrical force, right? And Coulomb's law just says that it is going to be equal to k q1 q2 over r squared. So what are we talking about? If you have two charges, right? Let's say you have your charge of q1 and then q2, right? You can calculate it using Coulomb's law based on how far they are from each other. Okay, and then you have some constant. This is what we call the Coulomb's constant. Coulomb's constant, and is going to have a value of 9 times 10 power of 9. If you want to know exactly what's the unit, we can look at the equation and we can say it is going to be, it will have the units of Newton meter square, and then Coulomb power of negative 2, right? And it's actually equal to 1 over 4 pi epsilon naught. Okay, where this epsilon naught is the permittivity of free space, right? So that is just on force, electrical force alone, but by the end of the day, that this force is a vector. So what that means, you can add or subtract vectors. But that also means that these questions can be in two dimensions. If it's in two dimensions, then you have to be reminded of Pythagoras theorem and trigonometry, just like how we dealt with Newton's laws and our dealings with forces. Okay, so let us just begin on the questions. All right. Okay, so let's look at the first question. Right, determine the electrical force between two particles of charge 1 microcoulomb and 3 microcoulomb separated by a distance of 30 centimeters. Now, if it doesn't have any sign, that would mean that it's going to be positive, and this is going to be positive. Remember that force is a vector, and if you're determining some vector, you need two things. You need magnitude and direction. Okay, and then the distance is 30 centimeters. You should convert this into meters. So that means that my 30 centimeters, which is equals to r, by the end of the day, it's equal to r. It is going to be 0.3 meters. You have q1 to be 1 times 10 power of negative 6 microcoulomb. And then you have q2 to be 3 times 10 power of negative 6 coulomb. All right, so we are looking for the electrical force, and the electrical force is just F. We're going to determine. I'm looking for its magnitude for now, right? So I'll have 9 times 10 power of negative 9, and then I have 1 times 10 power of negative 6, and then I have 3 times 10 power of negative 6. Okay, and then of course I have r squared, which is just 0.3 squared. Okay. Okay, so if we key that in, what we will find is that the force is going to be 0.3 Newton. But that is not enough. This is merely the magnitude. If we were to draw this out, let's say this is 1 microcoulomb, then we have this to be 3 microcoulomb, then because they're both positive, they are repulsive. So let's say repulsive. Okay. So its direction of F is going to be away from each other. So away from each other. So that means we have two paths, right? Our magnitude and our direction. Okay. Okay, so on the other hand, here we have an example of a question where we have opposite charges. Here we have positive charge and the other particle is negatively charged. So if we were to draw it out, again, I highly advocate you to draw it out. I'll have 1 microcoulomb and then I have negative 3 microcoulomb. And as we've learned from a very young age, if we have opposite charges, they are going to be attractive. Okay, so because we have maintained the values 1 and 3, we know that the electrical force, the magnitude of the electrical force, is going to be the same as the previous question. But let's just calculate it out. I will write down the solution step by step. I will have 1 times 10 power of negative 6, and I have negative 3 times 10 power of negative 6. And the distance between them also maintains the same, which is going to be 0.3, but I will have to square that to find the force. So then what we find is that the electrical force is going to be going to have a negative value compared to the original question. So I will have negative 0.3 Newton. Okay. Instead of saying it away from each other, we will say towards each other because they are attractive. Okay. So what can we conclude from these two questions? If I have my force to be bigger than 0, which means it's positive, then the electrical force is going to be repulsive. If I have the force to be less than 0, being negative, then I have an attractive force. Okay, and this is true if I have both negatives as well. If I have negative 1 and negative 3, negative 1 times negative 3 is positive 3. If it's positive, then it's going to be repulsive. So what that means, if I have a negative negative pair or a positive positive pair, is going to be repulsive. In other words, like charges are attractive, are repulsive, and unlike or opposite charges will have attractive forces. Okay, so that is on this part, and then after this, we want to do a problem on 2D, okay, where we deal with forces. We might have to use sorry, what do you mean? Sorry, the trigonometric functions as well as Pythagoras theorem. All right. Okay, so here what we have is a 2D case, right? We're still working on Coulomb's law, but instead we have a case of 2D. Now, what we want to do is to only consider two particles at a time, right? So let's look at the question. 3 charged particles are arranged as shown in the diagram. Determine the Coulomb force experienced by Q2. So you are focusing on Q2, okay? Focusing on Q2. If Q1 is 2 microcoulomb, so 2 microcoulomb positive, and then I have Q2, let's change the color to yellow. Let's not use yellow, let's use black. I have positive 3 microcoulomb, okay, and then I have Q3 to be positive 4 microcoulomb. Okay, so bear in mind they're all positives. Okay, so if we only consider Q1 and Q2, then the force that we get is going to be downwards because it's moving away from each other. And then if we only consider Q2 and Q3, is going to be again away from each other. Okay, so we will have to find, let's call it F1 because it's interaction with Q1, and then we have 3. So then if we want to find the magnitude, we'll have to use Pythagoras theorem. And then if we were to find the angle theta, we will use trigonometry. Okay, so let's do the first one, which is F1. I'll use red. If I were to find F1, again, I have 9 times 10 power of 9 as the Coulomb constant. And then I have the first charge particle, the charge of the first particle, which is positive 2 times 10 power of negative 6. And then, of course, I have Q2, right? If I have to, the Q2 will have a charge of positive 3 times 10 power of negative 6. And then the distance between Q1 and Q2, which is R1 is just 0.3 squared. Okay, so you can key that into your calculator, right? And what you are going to find is, let's see, 0.2 and 3, I will have 0.6 Newton. So then I have F1 to be 0.6 Newton. Okay, I just want to label, this is K, this is Q1, Q2, and then this is R1, right? So moving on, I want to look for F2. Again, F2 will have 9 times 10 power of 9, and then I have Q3 instead. So I'm going to have positive 4 times 10 power of negative 6. And then I have Q2, which is positive 3 times 10 power of negative 6. And then the distance between them, which is 40 centimeters, which is 0.4 squared. Okay, so if you were to key that into your calculator, let me sleep that. If you were to key that into your calculator, what you'll find is that the force between Q2 and Q3 is 0.45 Newton. Then I can find the net force using Pythagoras' theorem. Okay, I will have 0.6 square plus 0.45 square, and that gives me a value of, let me check, 0.75 Newton. Okay, so that's the magnitude. What about direction? Okay, so direction, I will have to use, let's see, I can have tangent theta to be opposite, so F1 over F2. That means I can have theta to be the arctangent or tangent power negative 1, opposite of tangent, F1 over F2. And that gives me, let's see, let me just substitute the values. F1 is 0.6, F2 is 0.45. Okay, and that gives me an angle of 53.13. 53.1 degrees. So what's the direction? It's in the third quadrant. So it's going to be below the negative x-axis, assuming that this is x and then this is y. Okay, so what we've learned at this point is that when you have a 2D situation, number one is that you want to consider only two particles at a time, and then use Pythagoras' theorem to determine its magnitude. And at the same time, you use trigonometric functions to find its direction, and you should draw it out so that you know what direction it is going to.
Now we have a new problem where not all of the charges are positively charged. In the previous problem, we have all of it to be in positive charge, and thus they move away from each other. In this particular situation, on the other hand, we have Q2 to be negative, but I remain all the values to be the same. Again, we want to consider only Q1 and Q2, and then Q2 and Q3. Q1 is positive, Q2 is negative, therefore the forces are attractive. Q2 and Q3, again, one is negative and the other one is positive. So what they are going to be attractive, and thus we can write down F1 and F2. And thus the net force is going to be in the first quadrant. Okay, because I remain all of the values to be the same apart from the charge of Q2, the values are going to be the same as before. We can see here F1 is 0.6. For this particular case, F1 is simply going to be negative 0.6. I write down the calculation here, but we know for a fact that it's going to be negative 0.6. Mind you, that the negative 0.6 does not represent that it's moving in the negative y direction. It simply means that it is attractive. The force between Q1 and Q2 is going to be attractive. Okay, so here's the step-by-step solution. I have my substitution as well as the final answer for F1, which is again negative 0.6 Newton. This is the same case for F2 because again I've maintained Q2 to be negative 3, the magnitude is 3, and Q3 to be 4, which is positive 4. And the only difference from previous question is that it's going to be a negative 0.45 Newton. Okay, so again I'm writing down here the step-by-step solution, the substitution of the values, as well as the final sort of answer for F2. We can repeat the same procedure as before, where we take Pythagoras' theorem and inputting the values, but bear in mind when you square a negative value you have a positive value, so its magnitude is going to remain positive. That means the F net is still going to be negative 0.75. Again here Q3 is still 4 microcoulomb, Q2 is negative 3 microcoulomb, and again same values, different signs. Okay, then I can calculate the net force. I just use Pythagoras' theorem and it will give out 0.75. But because we have drawn it out, we know that in this particular case the net force is going to be acting in the first quadrant, or the vector is going to be in the first quadrant. So when we calculate the angle, right, the angle is going to be coming from above the positive x-axis, and we will denote that, we will write that down. Okay, so again square of negative are positives, so we will still have the same magnitude values for F net. Again we can calculate theta, right? It should give us the same value for angle. The difference is that it is going to be above the positive x value, positive x-axis. So I hope that that clears things up on how we treat Coulomb law problems in 2D. This can be very complicated if it involves multiple values. Multiple point charges. Okay, so it's so important to draw it out. Here I'm showing you, okay, when I draw it out, because they're repulsive, they're moving away, and in the second part we have both of them to be attractive. Okay, and I've done that simply by changing the sign of Q2. I've maintained all the same values, I changed the sign, and we will denote that by putting our answer as above the x-axis.